Hey guys, I'll just let a few guys roll in. Seems like a few more people joining. I hope you can hear me all right. Just let me know if there are any issues with hearing me in the chat box if you need to. Look, I'll get started. So yeah, thanks for coming, guys. Welcome. For those who don't know me, Ben Lewis, Geofabrics. I'm the water and mining manager. So that involves some technical sales primarily and supporting consultants and regulators and all sorts, mining people. So yeah, I'm sure I know a few of you, but just keep in mind there is a Q&A chat box there. You can ask any questions in. I'll look at those at the end. So plug your questions into there if you have any. And this session is being recorded. So just keep that in mind, and it will be available on our website, I believe, after, if you're keen on that. I can share the PDF if you're really interested in that. So just let me know. I'll probably share my email at the end so you can contact me personally. So today, I'll just be talking about developments, design and selection of HDPE, geocomposites and cushion geotextiles, and a bit on conductive geotextiles, and trying to link that to, I suppose, risk management in waste and water and mining applications primarily, not so much landfill, but definitely mining. So hopefully that's relevant to a lot of you. So I'll just introduce you to the GRID. The GRID is our Geosynthetics Research and Innovation and Development Lab based in the Gold Coast, and we are encouraging people to use that as much as possible. We do a whole range of geosynthetics testing for, I suppose, compatibility with liquors, waste, strength testing, immersion testing. Could be with HDPE, could be with cushions, could be with reinforcement. And really the primary objective is to link to site-specific performance and prove longevity, essentially, in higher risk applications. Relying on technical data sheets these days is becoming less and less relied upon, essentially, primarily because there's not enough data to show you how they are going to perform long term. So keep that in mind. That's available. Got the GRID email on there, but you can reach out to me at any time if you want to do some testing. But in terms of liner specific performance testing, we do a whole range of stuff. We're doing UV testing of geotextiles and liners, chemical compatibility and liner protection testing of polyethylene liners. So that's HDPE and LLDPE, as well as GCL liquor compatibility testing. And we're doing drainage testing, shear box testing. So a whole range of stuff that's relevant to the mining industry to show you how it's going to perform maybe on a slope or with the leachate that you're expecting. So we do have a lab report which shows you what we're capable of, and I can share that with you separately as well. So in terms of the liner testing, the immersion testing, we can either do 1 month screen testing, which allows you to really compare materials. So it is a quick test. Basically, it's thin film accelerated testing where they thin the membranes down, accelerate that degradation process, or you can do it over a 12-month period, which allows you to predict longer term lifespan of those materials. Obviously, time doesn't permit to do that, so sometimes a screen test is adequate, but you do need time up front of these projects to do this type of stuff. So engaging with us early on is critical. Obviously, thermal testing, UV, interface shear, and cushion testing are the primary tests I'd suggest that we do in the lab in the mining sector. So as I said, you do need time up front. So it's something that needs to be considered in feasibility, or by the time you get to the design phase, it can be even a bit too late. So just engage with us, keep in contact. If you've got any questions about durability concerns, we can work through that with you. But essentially the aim is to hone and give you a product which is going to last the standard time in your application. And essentially it leads to cost-effective designs and giving confidence that it's going to last. Sometimes it might cost you a few dollars more, but it's going to last, and you're going to have minimal maintenance on these materials. And in terms of mining applications, the higher risk projects where you would consider doing this might be tailings dams, residue ponds, filtered tailing stacks, processed water ponds, hydrocarbon bun storages, maybe less mining there, but brine storages where you've got high temperature and high saline conditions, heat leach pads, and these all have different exposure risks. Could be chemistry from heat or heat from chemistry, sun exposure, UV, shear, stresses from trafficking or from loads from heat leach pads, etc. So there's a whole range of exposure risks that are different depending on the application, and so you do need to consider what you're dealing with when you're selecting appropriate materials and, I suppose, specs on those materials as well, because not all HDPE performs the same. There's different grades depending on what you're dealing with. And just looking at specifically at the tailing storage facilities to give some context to why the industry is probably heading to where it is. And by the way, I took this from Circular Mines, so a colleague of ours shared this with me. But effectively, the industry is heading towards a lot more lining of tailings dams that might have historically been unlined. And some stats for you: 10,000 tailings storage facilities globally, 100,000 active abandoned and closed facilities. So primarily the closed ones would be unlined. 200 failures over the last 5 years of tailings dams, and that's of failures that we know of. There's probably been others which haven't been published. 2,000 casualties, 20,000 kilometres of rivers and streams polluted. So it's just giving you a bit of a feel about why the industry globally is heading towards lining of tailings dams. It really comes down to mitigating risk of these issues occurring. And in terms of how these failures are occurring, this chart just shows you how, what's the primary cause. Earthquakes, the biggest cause, maybe not in Australia, but certainly overseas. Slope instability and seepage, large causes, and they're probably the most relevant issues that we can have an impact on with geosynthetics. So obviously slope instability is caused by maybe slopes that are too steep, saturated, and obviously seepage impacts that, but it also impacts contamination of groundwater streams. And we can generally prevent both of those through good design. This risk matrix here is just something I developed to show you, I suppose, the risks of each of these storage assets in terms of failures and risks in terms of what's at risk on the performance of the liner. So I'll just go through a couple of these. TSF, say we're looking at a tailings dam which is holding inert waste. You would expect it to have less stress on the liner in terms of exposure to chemistry. So it's got lower degradation risk, and it's got tailings dams generally have lower hydraulic heads because you've got quite a lot of soil in there. So lower hydraulic heads leads to less risk of or lower flows through defects, which is good. But in terms of the higher risk with that particular facility, you've got risk, they're pretty deep facilities, so your embankments are at risk. If you have a failure, it could be catastrophic. And it's also a very long-term asset, so you need to think about how it's going to perform long-term and how that geosynthetics holds up over time. And now if we're looking at the heat leach pads, they've got very low hydraulic heads as well. It might only be a 300 mil deep, similar to a landfill, I suppose, but 300 mil deep liquor sitting over the liner. And it would be considered a short-term asset, so you don't need to think such long-term. In terms of the higher risk, You've got heat, pH risks. It could be acidic, could be alkaline, and the risk is that you're losing this valuable pregnant liquor through leaks. So you really do need to have a bulletproof lining system, otherwise you be losing money at the end of the day, and you could essentially pay off a better quality lining system just through saving on leaks. So I won't go through other ones, but you get the idea. So how do we limit the risk of dam failures? And I've touched on the causes, the primary causes that we can impact: slope instability and seepage. And when you combine those two, it can be catastrophic. But the solution, as I've mentioned a couple of times, is essentially containing and securing these dams through good design of geosynthetics. Tends to result, at least in the tailings industry, results in more volume required in filling these dams quicker because it's holding more water than it probably used to. But there is ways around that as well. You can introduce drainage above the liner and either drain your tailings within the facility and capture that water. And actually, we've heard recently on a job in Queensland where they were using drainage nets above the liner within a tailings dam, and they were getting 10% better water recovery from that net and reusing it. So 1, you're getting the water back; 2, you're removing the hydraulic head pressure on the liner; and 3, you're reducing the risk of, or you're limiting the risk of holding water, which adds to the liquefaction risk of tailings dams. But effectively, we're lowering the risk, and results in less contamination to groundwater when you line. So essentially, the extent of the liner system comes down to your acceptable risk and acceptable leak risk and what you're trying to limit. In terms of different lining profiles, there's a few, but I've tried to put in the 5 primary examples. I mean, at the very basic end, for a shallow irrigation or agricultural water storage, tends to just be single liner HDPE. At the extreme end, you've got double composite liners, which would be a HDPE plus GCL with a net, and then another layer of HDPE and GCL. And that's probably pretty rare. But as I said, there's another job in Queensland recently, which included one of these systems, and that was for a brine, saline water at about 40 to 50 degrees C. So it does depend on proximity to residential as well, and the appetite for, I suppose, leaks that they're willing to accept. And it also depends on your hydraulic heads, etc. So I can share. You'll get a copy of this, and you can ask any questions at the end. How are leaks occurring? They're occurring either through short-term damage or long-term degradation damage. And in terms of the short-term damage, it's occurring from poor welding, puncture, heavy machinery. Could be drainage you're placing over the primary liner, or even placing protective material over the top. You can damage while you're placing it. So it's generally an installation process. It's worth noting most of the defects are occurring on the floor of these assets through foot traffic or machine traffic, and also that 70% of your defects occurring on panels between welds, while 30% are only on the seams. And that's important because depending on the job, you might only find that it's a requirement to test the seams, which is easy enough, but it's a little bit more challenging if you don't have the right preparation and materials to test the panels. But we should be testing panels because that's primarily where your leaks are going to occur. But it just does tell you that seam testing alone really isn't adequate anymore. There was a good paper here, which I've referenced here, where they looked at over 7 million square meters of HDPE installations, and they found an average of 7 holes per hectare. And that's quite a lot. It's probably gone up over the years, I think, probably due to the better testing methods. But it's, I suppose, another cause for, or reason, that we should be testing our liners before we're commissioning them. How do we minimize the risk? It's by design. And just a quick stat here. The chart on the left is for diffusion rate, hydraulic conductivity through the membrane, through a membrane, a 1.5 mil HDPE, and on the right is a leakage rate through defects. So on the left, 3 meter hydraulic head pressure over a 1.5 mil HDPE, you'd expect us to have about 80 litres per hectare per day through that membrane without any defects. Rather, through a 3 meter head pressure over a 2 mil hole over a sort of porous subgrade, you'd expect 1,300 litres per day through that hole. So you can see it's the defects that really cause the bulk of the leaks, essentially, and that'll come up later. In terms of long-term damage, you've got UV, thermal, and thermal can be from natural, from sun, or from chemistry-generated heat. You've got chemistry, low and high pHs, heavy metals, radioactive materials, hydrocarbons, and you've got physical stresses, which could be from stress from slopes, from elongation, earthquake settlement, placement of cover soil. So there's a whole range of things we can look at to limit stress on your membrane to ensure long-term performance. So preventing leaks with cushion geotextiles, all HDPE will expire at some point due to stress cracking. So if we can limit the stress cracking or improve the performance of the HDPE, it should be done. But what we do in the lab, we do a cushion test, which is effectively profiling up the membrane with a cushion geotextile, loading it up with a site-specific load and compressing it against the expected rock or drainage layer which the cushion and membrane may be in contact with. So if you've got, let's go back to this picture, you can see they've got drainage over the liner here, which has got a cushion between it, or geotextile, and the objective is to limit strain to an allowable limit to prevent cracking over time. So we do that test in the lab, and it's essentially what they do, by the way, is they take out this thin film which has been loaded up. There's a little thin sheet in there between the membrane and the geotextile, and they run it through a strain distribution profile. And what this does, this chart here, essentially show you, and this is the extreme case, obviously, but you get 103 holes with no protection and 47 holes with protection. So it's a massive reduction with geotextiles. But what we try to do is really hone what geotextile is going to be most appropriate for your rock or your maybe a rocky subgrade. So just quickly looking at this chart, the red solid line and the red dotted line. So the red solid line represents a 600 kPa compressive load over a rocky subgrade, particular sort of grading of rock with no geotextile, and that induced a strain of 25% on an HDPE. Now, HDPE tends to have a strain limit, or we're trying to limit that localized strain to 6%. Sometimes it's 2%, depending on the engineer. And you compare that to an A44 cushion protecting that HDPE under the same load with the same rock, it brings it back to about 12%. So it's a huge reduction in strain, although it's still above that limit. So that what that does tell us is that we'd have to increase the geotextile grade to something that's a bit heavier. And then we took it one step further because we're trying to understand what impact the type of geotextile had, aside from just its mass and technical data. And we tested about 40 different materials from all over the world and categorized them into continuous filament polyester, polyprop as well, and staple fiber polyprop and staple fiber polyester. And what it essentially told us was that continuous filament polyester for an 800 gram mass induced a strain over a certain HDPE of 6.5%. And we compared that to a staple fiber polyester geotextile for the same mass, only induced a strain of 14.3%. So it really just highlighted that you can't just look at mass for performance of cushion protection. You really need to look at how the product is manufactured, and it was quite clear that continuous filament polyester geotextiles perform far better than anything else. This plot on the right is just basically a curve plotted through all the same plots without considering anything else, just really looking at mass versus maximum strain. And really the correlation is quite poor. It's 0.4 versus around 0.9 when you start to consider the actual manufacturing process. Prevention of leaks, spark testing. I won't spend too much time on this, but there are options out there. You can do conductive backed HDPE. We've got a conductive geotextile, bitumen C. Effectively, you're placing this conductive medium below your primary liner, connecting a conductive broom on a cord, clipping it onto the edge of your geotextile, and then walking along your primary liner. And where there's a hole in the liner, you'll get a spark jump and complete the circuit onto your broom, and an alarm will go off and you'll effectively patch it. So it's a really simple, dry and accurate means to test liners and panels between seams, and it's drastically improving your CQA methods. Until recently, I think the idea was that it was better for flexible membranes because you do want that intimate contact with the primary liner and the conductive layer. But essentially, if you've got a wrinkle there, you can just compress it with your foot, and we've found that it's quite effective. And there's ways to limit your wrinkles through certain methods, and I'll touch on that as well. I'll move on from that. So in terms of HDPE and industry improvements, I'll give a bit of an intro. Geomembranes are essentially flexible polymeric sheets employed mainly as liquid or vapor barriers. And they're commonly 1.5 and 2 mil thick in the higher risk industries. They can do 2.5, 3 mil thick, but you'll find, although the benefit is there, the welding installation is much slower, and generally it's not done. And the variations in the membranes comes down to the resin, the formulation and the additives, and the thickness. And these variations are basically establishing the durability and resistance to chemistry, UV exposure, thermal, all those types of things, oxidation. So really the key is to understand what your exposure risk is before you select whether it's HDPE or LLDPE, but also when you're drilling down into the performance of each of those as well. There are industry specs you may be familiar with. For HDPE, it's GRI GM13. For LL, it's GRI GM17. But these days, that would be considered probably more appropriate for your lower risk water applications, where you're looking at higher risk applications. Maybe you consider looking at certain properties like an increase in stress crack. I think in the GRI GM13, you've got certain HPIT, SOIT, and stress crack resistant values, which for the high end HDPE at least, vastly improved on. And you can see that in the immersion testing and performance over time. And there also is a BEPM guideline for the landfill space, which I'm less familiar with, but it's highly prescriptive. And New South Wales and SA are also following that now as well. So in terms of when you might select HDPE or LLDPE, 80% of applications would be HD, but with that you're getting a wide range of chemical resistance, weld strength, and it's pretty inexpensive. That's why people tend to go towards HD. But it does have stress cracking resistance issues depending on the grade, thermal expansion and wrinkle issues, puncture, strain, wind affected. It's quite light, obviously. So there are some issues with it, and it does need to be protected, which is where the design comes into place, but it's still cost effective. And it does have those, durable chemical resistance properties. Whereas LL has better differential settlement properties, so good multi-axial strain, better temperature management, tends to sit a bit more flat, less wrinkles, and it's more flexible. So probably more appropriate for your capping applications and differential settlement applications, which is what we tend to see with landfill as well in their capping. In terms of the testing, I touched on this earlier. We can do immersions for 3 to 12 months with HDPE and predict long-term performance. We basically immerse it in different temperatures, 40, 60, and 80 degrees, to try and accelerate that process. And it's really there to compare these performance criteria, which is touched on: HPIT, stress crack resistance, and assessing how those perform after exposure. So I won't dig into that again. I've touched on that already. And in terms of lifetime of these materials, or HDPE specifically, compared to what is available on the market, we are aligned with Adafil, so I've shared some Adafil information here. But if you were to look at the standard GRI GM13 specs in a temperature of, say, 70 degrees liquor, now there's limited information I'm sharing here, but this is just for comparison's sake, you'd expect maybe only a 4-year lifetime. And you compare that to a superior product, which has got better stress crack resistance and other performance properties, you might get 2.5 times the life out of it. So it's certainly worth considering, even in low risk applications, if you want to get a longer performance out of it for not a huge cost differentiation. And so I'll just touch on white geomembranes and texturing, because they do have some benefits aside from just aesthetics and slope interaction. White HDPE has been found, this is nothing new really, but and this is some pretty old data actually pulled out, but it does reduce wrinkling height and frequency when you use white membranes. So that's good for, well, it's easier installation. It makes it, it keeps it cool if it's a hot environment, so you can install maybe during the day rather than at the night, in nighttime. It reduces the temperature, so it slows that thermal aging process. And there's some stats here as well. So these stats here relate to a thin white coating, by the way. So we could actually increase the thickness now with these HDPE to maybe 50% of the membrane, and there's even better improvements with these properties. But just looking at thin coating, we're seeing 43% less frequent wrinkles, 33% drop in wrinkle height, and a 27% drop in temperature during the day. So significant benefits, and I've touched on what they are. So now we're actually promoting increasing that thickness to maybe 50% of the material, because you get even better temperature drops and better properties with wrinkling and frequency of wrinkling. And in terms of texturing, yes, you would use texturing if you wanted to place your HDPE or LL onto steeper slopes, but it actually helps with wrinkling as well. There's this chart on the right was done by Giroux back in 2005, and just through texturing, so textured black versus a smooth black, they found a wrinkle reduction of 28% and a 50% drop in wrinkle height of 50%. Not only is it, I suppose it's better, it's good for installation, it's good for wind uplift, it's providing more intimate contact with your subgrade, which helps with flow rates through leaks. So there's just that many benefits you get out of using the appropriate color material with maybe a texturing. And so when you're comparing textured white to a smooth black, it's 50%, 57% less wrinkles and 37% drop in temperature. So I'll move on from that, but I think you get the idea. So geocomposites, I think the last topic I'll touch on, but geocomposites are drains that collect and convey liquids and gases. They're manufactured by bonding a compression-resistant net comprised of 2 or 3 ribs, sometimes laminated with geotextiles. So this picture here, hopefully you can see my mouse, the top left picture is a triplanar net. You can see this big thick rib running vertically with the thinner ribs running on either side of it, top and bottom. So that's a triplanar net. And the biplanar is effectively 2 ribs, same size, running perpendicular to each other. Now, the triplanars tends to have higher compressive strength. They do tend to only allow water flowing in one direction, so you do need to place the triplanar nets in the direction of the slopes to allow water to permeate in that direction. they're less creep impacted, and as I said, single flow direction, but they are better for cyclical loads. So if you wanted to put this under a road, you would probably be using a triplanar net. Biplanar nets, 2 ribs, as I said, they allow for radial flow, so better probably for higher hydraulic heads, maybe water storages. Lower compressive strength though, higher elongation generally, easily affected by creep under high loads, probably better for static loads, and you will get more geotextile intrusion due to the makeup of the material. You can imagine if you've got a geotextile over the top of this triplanar, you won't get as much pushing into that flow path. What's the primary function? Well, in the mining sector, trying to relate this back to sort of mining applications, but reducing hydraulic head on liners if it is above the liner, that is, and provides less pressure over the hole, so you get less leaks, or slower flowing leaks effectively. Reclaiming water, as I said, 10% better recoveries we're hearing on other projects. It spreads the load onto the liner if it is above the liner as well, so it almost performs like a cushion. I believe we've got some data from that on the Canman 2 project from years back. So that's kind of ideal for heat leach pads where you want some drainage and some cushion protection on your membrane. Reduces thermal impacts. It's obviously not exposing your liner directly to the sunlight, so you see less wrinkling and wind uplift problems on your primary liner. And it helps with foot traffic over the liner as well, and wildlife personnel. So some benefits that you probably don't think about. In terms of drainage below the liner, we can quantify leaks through the liner, so it gives you an ability to qualify your performance of your primary liner. Removes piping and erosion risk below the liner. Gives data to your engineer of record on site. Gives them a bit of confidence in how it's performing. And you can actually assign action leakage rates for live monitoring. So as I said, you can live monitor your liner, so then you can understand when it's underperforming or performing as it should. Reducing your risk of risk for the asset owner in terms of failures and contamination of subgrades. So ticking that box with the EPA, and it provides long-term data on your liner, as I've said. In terms of limitations, considerations, and design risk, so you're looking at, generally we consider compressive load capacity. Higher the compressive load, the less the flow rate would be. Low interface shear on slopes. It changes with what your, I suppose, your laminated material is. Sometimes you obviously have naked nets, and sometimes you've got a geotextile on the net, so you need to consider how that performs on your slopes. Peel risk, is the geotextile going to peel off and slide as you place fill over the top? And I'm just really reeling off some considerations more than anything. Geotextile degradation, covering before it starts to degrade with UV, and you're obviously going to get some intrusion of the geotextile depending on the thickness, so that will impact your flow rates. The resin, I mean, not too many people think about HDPE resin performance in nets. There was a job done recently in Queensland, done by Red Earth Engineering, and they made a pretty heavy-duty HDPE net, and you rarely see that because there's not too many suppliers that have capability in doing it. But it does tend to have impact on the creep, and I suppose the creep over time of the HDPE into the flow path. Biological clogging affects flow rate. Geotextile, whether it's heat set or needle punch, detects your flow rate. Geomembrane type. So different geomembranes also intrude. So LLDPE tends to intrude a bit more than HDPE because it's less stiff, and reinforcement also tends to be a bit more flexible, so it will intrude a bit more. And you can see the impact on the right here from a non-woven needle punch geotextile versus a heat bonded geotextile. So non-woven needled are good for cushioning, but not necessarily for laminating. In terms of net design, look, this might get a bit technical, but I'll run through it as best I can. So flow capacity must be generally, a flow capacity of a net must be greater than the leakage rate or your action leakage rate that you've set for that asset. Otherwise, if it can't handle the flow rates, it'll choke the flow and you'll get head pressures on your subgrade or your secondary liner, and then that will risk leaking or going into your embankment. So you're really trying to keep, your net has to keep up with the leaks that you're expecting. So we can work out what the Q allowable will be. So we can work out what the ultimate flow capacity of a net will be through transmissivity testing in the laboratory, and then we can apply some reduction factors to account for site conditions. And those site conditions might be intrusion, deformation of the core. That could be from geotextile, basically pushing in. It could be creep of the core, it could be chemical clogging, and it could be biological clogging. So there's a number of factors there. And there is some information on this. You can do testing to actually work out what these reduction factors are. But as a general guide, you could come to this and assume best case or worst case and apply it. But for a secondary leachate collection geocomposite in a landfill, the reduction factor multiplied comes to about 16. So it's a reduction factor of 16. That's significant. But maybe for a worst case, maybe you do apply that, particularly in mining and landfills. So it's just, I suppose, some considerations, because that allows you to work out what type of net you might want to use. And in terms of your action leakage rates, that is generally set by the asset owner or the designer, depending on the risk they're willing to accept. So landfills, you can set it as de minimis, which is essentially 10 litres per hectare per day, which is unrealistic. That's essentially only allowing for no leaks, only through vapor diffusion. I would say that's unrealistic. Otherwise, 50 to 200 leaks per hectare per day is quite common for an action leakage rate. For a design leakage rate, maybe they at the point which they have to take action. It's a bit confusing actually, but so at the ALR, you maybe monitor it closely and assess liquid compared to primary leachate. Otherwise, you can set a higher leak rate for when you have to take action and stop filling, maybe start thinking about continued monitoring or stop adding in waste or water. And maybe when you have a really high leakage rate, and this is really for landfill, keep in mind, where you've got low hydraulic head pressures over the liner. So 1,000 is quite a lot, and the leachates are quite aggressive. But then maybe that's when you start to take real action, remove overburden and repair. Mining and water space is probably gets away with a bit more. But a bit of research suggested that in the US, the average ALR comes to about 5,000 litres per hectare per day. But it is dependent on the contaminant, the risk and the consequence of the leaks. But that really comes down to what your head pressures are. I think the example here considers, say, 2 holes per hectare is acceptable. And then based on that, you can work out what the leakage rate might be. Now, the example here I've got is, so it's quite difficult to accurately select grades of geonets without specific transmissivity testing. Not all suppliers have a huge amount of transmissivity testing. There's always one value on a data sheet, but that is only specific to the compressive load and the hydraulic conductivity, hydraulic gradient, sorry. So this design example, I've said, calculate the factor of safety of a biplanar 6.3 mil net with flows between 2 HDPE liners. And the aim is basically to get a factor of safety greater than 3. The compressive load is 30 meters, which is approximately 525 kPa. So firstly, we want to define the action leakage rate, the ALR. And let's say 2 mil holes is the 2 mil holes is the acceptable amount of holes that they're willing to accept. And you can actually work out roughly what the flow rate would be based on that by converting it into litres per hectare per day. And that basically comes to these numbers down here. So we've got Q required. So we have to have a capacity in the net for that flow rate, which is 8,000 litres per day per hectare, converted into flow per square metre per second. Now, this chart on the right here, by the way, which I think I've got over here as well, is a chart from way back in the day, but it's showing flow rates of a particular net under a compressive load for different hydraulic gradients. So as I said, a technical data sheet for a product might only have one specific value on there. So you really need these charts to understand what the transmissivity of a net is under different conditions. So continuing on with this example, most nets, as I've said, I've gone through that, sorry. So this Q ultimate here is the capacity of the net. So we've basically pulled that from the data sheet, used this chart to get that. Again, it's probably not going to make a huge amount of sense, so I will skip through this a bit. But we've worked out the transmissivity, and that allows us to work out a factor of safety. In this case, we've achieved a factor of safety of 21 with the specific conditions of the net and the site conditions. So hopefully that makes sense. I probably haven't done a great job of it, but you can run through that in your own time. There's a bit on GCLs. I'll probably leave it there, but what I will say, GCLs, I'll bring it back here. I'll just do 3 slides on it, and then I'll open it up to questions. We obviously produce our GCL, geosynthetic clay liner, in Australia. It's formed of a bentonite clay sandwiched between 2 geotextiles, and the geotextiles can change depending on the grade. But you can see the cross section here. This is our X2000, our higher end of our higher versions of our GCL, and it's got this secondary geotextile, this needle geotextile on the underside. On this picture, you can see the black woven. There is a black woven in this bottom one as well, but the X2000 and X3000 has that secondary or that tertiary geotextile needled on the underside. And that is important because it does have impacts on interface performance, interface shear performance, puncture resistance, and even swelling, ability to control the swelling in rainfall events. And this chart on the right, almost call it quits in a sec, but this chart on the right just shows you the impact of an X1000, which is just that woven geotextile on the underside, versus a non-woven or the needled fabric for X2000. So X2000 does get about 50% more interface shear performance than the X1000. So if you want to go steeper with your embankments with GCL, then you really should be considering an X2000 or something that has that additional resistance, shear resistance. I might call it there, guys, because I think see if there's any questions. Q&A. Doesn't seem to be any questions. If you want to plug in anything in, if there's no questions, I'll keep going because we do have 10 minutes left. Otherwise, plug your questions in. It doesn't seem like there are any at this stage. Otherwise, yell out. But I'll leave the questions there, and if you want to yell out, otherwise I'll continue on. Effectively, what it also does with that extra layer, it allows you to accept some kind of prehydration. So whether that's by design or by accident from rainfall, the X2000 would be the better option. GCLs typically do rely on hydration and swelling to perform as a barrier. So it's worth considering. You don't want to, if you do cover it with something like a Forticon plastic before we're covering it because you're worried about rainfall, you want to remove that prior to it so it can be hydrated from the top down once it's covered with soils. And I'm assuming everyone's aware that with GCLs you do need that compressive load over the top to limit the swelling long term. And I think GCLs are underutilized. Why do I say that? I think GCL is maybe misunderstood, or maybe don't understand their capabilities with the amount of testing we've done. So in terms of people worry about desiccation and drying, we do polymer modify ours with only like 1 or 2% of polymer, and that tends to assist with drying properties and desiccation. I mean, it is under 300 mil of soils as well, if you recall. So there is data out there suggesting that agricultural data showing that you can get the protection that you need from drying, even in really hot environments. Erosion of the bentonite below primary HDPE, we've got a whole range of testing. I think I've got a chart in a minute, but a whole range of testing to show that our GCLs do not erode, and that comes down to the way that it's made up with the polymer modification. It's actually literally bonded very well to the bentonite we've got. So it does come down to chemistry. It's not just a matter of adding a heap of polymer, because the polymers can wash out if you add too much. But wouldn't be too concerned about erosion with our GCL. And we've got tech notes to back that up. Chemical compatibility, I think there's a lot of concern around how GCLs and bentonites perform and swell or don't swell with different chemistries. But in reality, what you see with GCLs in maybe a higher pH solution is it'll start to limit the swell. And that can be bad, but at the end of the day, it's still, maybe instead of being 1 times 10 to the negative 11 meters per second, it drops it to 1 times 10 to the negative 9. So still in the realm of compacted clay liner. It doesn't completely destroy the performance. It just increases that hydraulic conductivity value. And again, we've got data to back that up. And again, perception of the confinement layer. Yes, there's cost and time in that, but protecting any liner, I mean, if I could, I would suggest all liners are covered if you can protect them. I mean, the good thing about GCLs is they don't need a cushion, got an inbuilt cushion. But if you can protect any liner, it's going to last a lot longer. Sorry, I should be opening this up into this format. How much time have I got? 10 minutes. Not long to go, guys. I haven't seen any questions come through, but again, feel free to ask anything. GCLs tend not to see as many small pinholes because once they hydrate, they'll swell up and fill those voids. So you tend not to get as many defects, but you will see a higher hydraulic conductivity value. HDPE is the least permeable solution when it has no holes because it has a very low hydraulic conductivity, yet it can often see more leaks than GCL when it's on its own due to the risk of defects during installation. So there are things like that you need to consider, and that's why GCLs really should be protected. And this chart here, this is sort of showing the impact of a composite liner effect with HDPE and GCL. Clearly the best solution in terms of mitigating leaks and flows. So you can see here HDPE, and this is probably more relevant for landfills with only a 300 mil of head pressure, but HDPE on its own, you'd expect maybe 3,000 litres per hectare per day. And that's entirely dependent on leaks, I understand, but this is just an example. Versus a composite liner, which is HDPE and GCL, only 0.3 litres per hectare. So it's a massive, massive difference when you're using composite liners. I'll just touch on this one. GCLs, we've done with ongoing 7 years of testing with GCL and seawater. So if you're concerned about performance with saline and our GCL, we do modify it with a certain polymer, which allows the product to perform long term. You can see the hydraulic conductivity has not changed over that 7-year period. I think the perception with polymer modification is that it hides the performance of the bentonite. And in some cases it does, and you'll see that through some GCLs having 20 to 40% polymer added. But we only add 1 to 2%, and it binds very well, so it really only enhances the performance of the bentonite. We've done a range of testing with our GCL in hyperalkaline solutions, diesel, seawater, calcium carbonate solutions, and you can see here None of these have dropped below that 1 times 10 to the -9 performance. Yes, they all vary in terms of how permeable they are, but you can see they still perform quite well. The worst performing solution was the hyperalkaline, but still well and truly above that, relatively impermeable product. This is the last one, I think. Yep. And this is just Techno. We've taken this out of our Techno, just showing you how good our GCL does perform when it comes to erosion. There's an industry standard for testing erosion. It comes up quite a lot in the industry with people concerned about GCLs eroding, and that's why a lot of people tend to like the option of putting a liner over the top of it, another liner over the top of the GCL, between the top liner. But in reality, we're confident, and we can show it and prove it, that the bentonite will not erode over time due to the makeup of the material. So I won't go on about that too much, but I think you get the idea. But that's it, guys. So I don't think I've seen any questions come through as yet. Q&A, here's one from Raybury. Are there any considerations for cyclical loading, such as tidal ponds that empties twice a day? Are you referring to GCLs? I assume you are. Look, I don't think I've got any specific data on it, but wetlands are commonly used with GCLs, with the cover soils. And I think they perform well. I don't have the data to share on it, but if you want to touch base, I could probably speak to our labs and understand cyclical loading. I'm assuming you're talking about GCLs and cyclical sort of levels of water and maybe hydration and drying. But probably can't answer that one as well as I should, but we can talk after if you like. You've got my email, so apologies. Well, if there's nothing else, there's my email there. All I'll say is, selecting cost-efficient materials really does come down to how long you want these materials to last. You could choose the cheapest material on the market, but it might only last you 5 years. And paying an extra 10-20% might get you an extra 300% of lifetime, if not more. So you really got to think about it long term, how to protect your membranes, and yeah, we can support you through that process. We can do lab testing, as I said. So just keep it in mind and touch base if you've got any ideas you want to run by us. That's it, guys. There's no more questions. I'll leave it there.